Well, thank you very much. Really glad to be speaking at the OpenFOAM Workshop today, just like last year. And this time I'm going to talk about a project I've been working on as part of the PhD University College Dublin in Ireland. We have given the name of learning constitutive models for mechanical tests with the autoprogressive algorithm based on OpenFOAM and Python. And I've been working on this with 3 other academics from University College Dublin. So in this project, basically what we want to do is we want to replace the theoretical elastoplastic models used in solid mechanics simulation with machine learning models that will be trained either from experimental data or from microstructural simulations. We hope that by doing that, the final uncertainty related to assuming a material model will be reduced and the accuracy of the results will be improved. But this poses several challenges, of course. And the most important one is that at the core our solution process, we have a numerical equation. And in order to make it solvable, we need, of course, the material model. But the material model maps usually strain to stress. So you think if what you need is a machine learning model that is going to map strain to stress, you just need a set of pairs, strain and stresses, so that you can run your synchronized algorithm for training it, and then you use a model. The problem is that in a mechanical test, we can measure the displacement and the boundaries. We can measure the loads and the boundaries. We can measure the displacement for the internal field, but we cannot measure the stresses for the internal field. So we cannot run a supervised algorithm for training machine learning models. So what do? We found several possibilities, and I found this very interesting algorithm in the literature called the autoprogressive algorithm for self-sim. You cannot see that self-sim over there. But basically, it's a generic algorithm. It's not even just applicable to material modeling. It's not for situations where you need an inverse method. And what it does is that it alternates using the global input and the global output that you know from a material test. It uses it or it alternates them, generating several simulations so that the final data set is used for training the machine learning model. And at the end of the process, you learn the local mapping that is governing the relations for the internal components. But as I discussed with Bill before, this explanation is kind of tricky. I don't really know it. So I translated it into the material modeling context. And in this context, the autoprogressive algorithm does this. So basically, there's 5 steps. The first step is we are going to select a machine learning model that we think that might be suitable for the application we are going to deal with. So then that machine learning model is going to be trained with a reference behavior. In this case, we are using linear elastic. And then with that machine learning model, we're going to run 2 different simulations. In the first simulation, we're going to apply the known loads. And the idea of this algorithm is that given that we are using an approximate machine learning model, and we're using the known loads, the final stresses from that simulation will be similar to the real ones, because they are going to be coming from the solution of the integration. And then we are going to perform a second simulation, but this time is basically the same simulation, but instead of using the known loads, we're going to apply the known displacements. And the idea here is that given that you're applying the known displacements, the final strains are going to fulfill compatibility. And for that reason, they are going to be similar to expected for real ones. So then, with the stresses from the first simulation and the strains from the second simulation, you will train the machine learning model as many times and deliver the process as many times as you need until you learn the real mapping. So that's exactly what we did in this project. So we got it a Python routine that basically has these steps over here. This is like a high-level explanation. But basically, we first, from a Python environment, we calculate the stresses from the expected strains. And this is a small modification because In the original paper, they don't use the expected strength. They use random data. We simply plug that. We're going to use the expected strength because we already have them. Then I am feeding a machine learning model. To begin with, I use a linear regression model. I will talk about it later because I already tested it with a neural network as well. And then all of this is being triggered from Python. For Python, I run a command. So I execute the first simulation, the multiple simulation. Then, and this is the part where I think the magic happens in this project, step T. After the simulation is run, we have a set of files where OpenFOAM stores the fields. So, but our machine learning models are implemented in Python. So we need the fields written in Python, readable files. So we use an in-house tool that we coded last year called the Python plot, and we simply convert the OpenFOAM fields into NumPy readable files that are literally usable. We can simply call them from Python. And then we repeat the same. So we run the displacement previous simulation and say the resulting string field from OpenFOAM, written in OpenFOAM format, we convert it into a NumPy readable file, and so that we can read it from Python whenever we want. And once we have those two fields, we simply can do whatever we want with that data and repeat the process as many times as needed. But this, as I implemented all of this, requires to build a couple of additional components. So the first one is the material model, because as I said, our machine learning models are implemented in Python. But what I think that our solid mechanics solver is solid for COM, which is a C++ code. When we started this project, there was no standard content. So there were several ways, but there was no agreement about what the standard was. So we simply coded our own application. We call it the Python PAL, or Python PAL for COM, or simply Python PAL. So what we're doing here is that we're literally calculating the stresses from the trains using Python. Well, that is wrapped in a solid for COM material load. I'm going to give a little more details later. And also we had to run an additional OpenFOAM utility. We called it the field manipulator. And it only performs one out of two jobs. It either converts the required fields from OpenFOAM to Python, or assigns the expected displacements as the boundary conditions in the boundary condition files, so that we can run the second simulation. And this is basically the same, but with a little bit of code, so that you can see what is happening. So first, as I said, we calculate the linear elastic stresses from expected stress, and that happens in Python. You can see that it's literally a Python command, but it is a Python command that is triggering a bash command. If I can explain it like that, so it's like we are artificially creating a bash or from Python. And also, and I am running that code called main.py. So the Python code is written somewhere else. And after I run that, I get the machine learning model, and I also get the cascaders. So, okay, after that, with the strains and the stresses, we simply feed the linear regression model to the data and we start running our simulations. So we run the first simulation, the node-driven one. Then we save the resulting stress field, but in Python files. So as I said, you can see here, this is the result from OpenFOAM, this file over here. I'm sure you have seen many files like this in your simulations, but after we execute this line over here, that you can see that's Python code, because it's simply a method from the NumPy file, the NumPy package. You can see that after executing this line in OpenFOAM, this file gets created, which basically has the same information, but it's readable from Python. And then we run the second simulation. So basically, this is also Python code, and this what is happening here is that I am assigning to the boundary condition files the expected displacements as boundary conditions. So after that, again, this is the result from the simulation, from the displacement-driven simulation, or one of the results, the strange field. And you can see that I simply run again one line of Python code that takes this file and creates this second file. They have the same information, but this is readable from Python. So once I have that, I have the stresses, I have this file over here and this file over here. I can simply load the information and retrain the machine learning model, and I can repeat this as many times as I want. So at this point, I would like to make a brief comment about Python PowerForm, because this is basically the library that allows me to do what I am explaining. So it is a header-only library that enables interoperability between Python and OpenFOAM. We introduced this library in the previous OpenFOAM workshop, the one in Cambridge. And as I said, it's kind of an in-house code, but we have already published it. So all the code is freely available. And what it does is that it creates a Python interpreter internally. And when we want to modify or to do something to an OpenFOAM structure or object, we send the data to the Python side, and also we'll send the code that we want to be performed on that data. And we can use, of course, on that code, we can use Python libraries. So after that, internally, it will execute that code on the data that we are passing, and then we can simply retrieve the information back from the OpenFOAM side. And of course, all the complexity is hidden from the user. The user will only see like a high-level method that is really simple and clean for using. So crucially, this library does not copy the data. So when we are transferring from OpenFOAM to Python and vice versa, we are not copying the data, and that's very good in terms of performance and memory. And if you want information about the details, there is a paper. We published this in the OpenFOAM journal with 3 test cases, and there are many details about the implementation. But I would like to talk about two of the two most important methods, in my opinion, about this library. The first one is pass to Python over here. This method, of course, is in the OpenFOAM side, and it receives a field, an OpenFOAM field, and a name. And what it does is that it literally creates creates a NumPy array in the Python side with this field, the field that you are passing, and the name that you are passing here. So after we execute this line with a field, we can do whatever we want to that field in the OpenFOAM side, in the Python side, and whatever we do there is going to be propagated back immediately to the OpenFOAM side, because they are sharing the underlying data. And the second command is execute. And this command simply, with this command, we pass literally this command over here is an attribute, and that's a Python code. And with this, we simply let the Python file know what Python code we want to execute on the Python side. So there is also a website about this library, the Python PowerForm. You can check it out if you want. It has tutorials. There are 2 tutorials. There are explanations about how to set up, and there is even a couple of video tutorials. They are no longer than 5 minutes, I guess. So, or you can drop an email either to me or to Philip if you want, if you are interested in using this library. So the material model that we implemented is as I said, is mapping the strains to the stresses. And in Solid for Foam, the material models have or the stresses are calculated within the material model class with a function called correct. And what we did to implement our machine learning method was modifying the correct function for one of the material model classes. And this is the modifications that we introduced. Literally, there is no more code than that. So what we're doing here is first, I'm passing to the Python side both the sigma and epsilon fields, which are the stresses and strains fields. And after I do this, there will be a NumPy array with the same information. One of them will be sigma on the Python side, and the other one will be epsilon on the Python side. Those will be their names. After that, I can do whatever I want with them. So there is the next command I execute is actually for calculating the stresses, and it executes the function predict, and predict does this. It's this over here. It's an extremely simple function, but you can see that it's also really powerful because it scales epsilon. With the scale strains, it applies it performs the prediction with the machine learning model, and then it scales the result back into the original range, and that's it. After that, the stresses are already calculated and they already exist in the OpenFOAM workflow. So this is the test case that we were solving. I guess all of you are doing solid mechanics. So it's a variation of the classical plate hole. In this case, it's a plate with a hole that is the left boundary is stuck to a wall, and it is being pulled, or there is a load applied on the right-hand side boundary. This is the load, 1.5 megapascals, and the mesh has 1,000 cells. And in this particular problem, what we wanted was to start with a really poor assumption for the material model and get to the final real result. So we're assuming that the material is a typical steel, but for creating the initial set of strain stress pairs, we gave it really wrong material properties. You can see them here. So the first machine learning model, the one with which we start the autoprogressive algorithm, or the data for training it was generated with these values: 100 gigapascals and 0.1 Poisson's ratio for the material, and the real ones are 200 and 0.3. So what we wanted was we wanted to check if the autoprogressive algorithm was able to get from the initial guess to the real value. And also this is crucial to this algorithm. I've been talking about a cycle of performing two simulations. One is load driven, the other is displacement driven. And this is not applied to this load, to the final load. Instead, the load is split into several load increments. So we applied here load increments of 1 to the 5 pascals. In the context of this algorithm, running the simulations for the 15 for all the load increments is called performing one load pass. And every time one of the load increments gets converged, the results in terms of strains and stress are added to the training data. So over time, the training data is increasing is growing in size. And so we limited internal iterations to 5. So it means that if we perform 5 iterations and the displacements are not, the calculated displacements are not the same as the expected displacements, we simply move on. The total number of load passes was limited to 10. We are not taking the boundary points. We are not including them in the training data or in the data generated on the fly. And we're also limiting the size in the training data to 30 load increments or 30 time steps. The linear regression model that I used for solving this problem was implemented in scikit-learn. And the problem is 2D, is two-dimensional. So, and some components of the strains are 0 in this case, and some components of the strains are also 0. So what we did, we implemented it twice. In the first one, we are simply neglecting all the zeros. And in the second implementation, we are not neglecting anything, but letting the zeros over there. And finally, some results. So you can see here these are the results for the displacement in the X direction for the simulation where I did not set up the displacement, but the load. So you can see 3 plots. One is the initial model. One shows the result from the initial model, then the result from the load pass 5, and the result from the load pass 10. You can see that there is a blue line. The blue line represents the expected behavior, and each red cross represents the results from one of the material points in my mesh. You can see that the initial agreement is really poor, but then after load pass 5, it is almost as good as the expected results, and the same for the load pass 10. And if I keep checking the rest of the variables, it's the same. These are the results for the displacement in the Y direction. Again, they are really improving over time. These are the results for epsilon XX, epsilon XY, epsilon YY, and always it's like the initial the initial guess is really poor, but then over time it becomes it really improves. And the results for the 3 components of stress: sigma XX, sigma XY,
and sigma YY. So, and this is this is already the final comment about this. Is the next step for me is implementing the same but using a neural network. But this is kind of outdated because I already did that and it also worked. The results are similar to the ones you already saw. And all of the codes are freely available in a GitHub repo in case you want to download and see what I did. Or in case you need to do something similar for one of your simulations, And finally, and this is the real challenge, I would like to extend this to elastoplastic cases. That's the real challenge, and let's see if I can make it for the next OpenFOAM workshop. Thank you very much. That's it.
Any questions? Very nice work.
Thank you.
Could you be clear how you build foundations and you mentioned the stress strain. Are you using regular samples for tensile test?
You mean for the do you mean for the regeneration of the expected data? Yeah. So no, we are solving it with the real properties or the real all of those data points come from the solution with the real material properties. And we are starting the process with a poor guess of the material properties. So, and we're taking them from that point to over time, it is learning the real behavior, starting from the really poor guess. So that's the goal in this, I could say this is a proof of concept, and that was our goal. Both are linear elastic solutions, but one of them has the real material properties, that's expected data, and for the other one, we started with a poor guess. Yeah, but no, actually, well, I think I should repeat the question. So the question here is how will I run this algorithm when I don't have a reference solution to use as the real values? And here, theoretically, what I hope is that I'm going to be able to have the results from DIC, digital image correlation, and from those results, I will have the strength field. So with the strength field, I can simply start running the simulation and all what you have seen. Yeah, you have seen.
Good. Thanks very much.
Yeah.
My name is Martin. This is coming from the Institute of Thermomechanics and Academy of Sciences. And the title of my talk is Simulating Laser Shock Peening in OpenFOAM. But actually, let's talk about hammers. In fact, laser hammers. So a little bit of introduction. And it's motivation of the work. Basically, in any metal component that you create, you usually create in a hot state. And the component comprises material grains, and then it cools down. And the grains shrink, which generates residual tension. And once you start to use the component, so you start bending it and stuff like that, the tension promotes initiation and then propagation of cracks. And usually you don't want to have cracks in your component. So what you can do is you can take a hammer and smash the material grains back together. So you will flatten them, elongate them a little bit, and you generate residual compression. And this residual compression, it, well, disallows for crack initiation to some extent and then for crack propagation. A little bit about history of this. Well, originally in 1908, there was the first occurrence of, the first documented occurrence of this peening when welders, and I think it was in State, they noticed that when they hit with the hammers fresh welds that are still warm, they improve their properties. And they use these hammers, peening hammers. Afterwards, the technology improved, and they said, well, let's not use a single hammer, let's use a shotgun instead, and hit the surface with a huge number of hard spheres, and shock peening will form. But now we are in 21st century, so we have lasers instead of shotguns. So where is the hammer when you use laser? We start with the target material with residual tension that's not wanted, and we put a duct tape on it. This duct tape is called ablative or sacrificial layer, but everything is better with duct tape. So we put duct tape and we apply the laser. So we have some laser beam, we focus it on the spot, and through instant evaporation of the duct tape, we generate plasma. And the plasma is actually our hammer in this case. We need to keep the energy of the plasma close to the material surface. So we put some transparent overlay. Usually we actually spray with water. It keeps the energy of plasma close to the surface. This is called confined laser shock peening, but it's not so important. And at the end, the plasma becomes our hammer. One may think that we have plasma, it will be hot, and we will need to put together some temperature, tension or temperature stresses and mechanical stresses. But in fact, the pressure that is induced by the plasma on the target is in order of gigapascals, and it's so big that we actually do not care about any temperature or temperature-induced stresses in a material, thermal stresses. Everything is purely mechanical, just through brute force. And on the right-hand side of the slide, I have some kind of spatial evolution. So this is -A to A. It's our area of application of the laser of the plasma pressure. Then we have a spatial evolution, rough spatial evolution of the pressure profile, and we have temporal evolution. Usually the laser used, it's in space, it's top head, and in time is Gaussian, but the pressure loses a little bit of its spatial properties, and it's in time is a little bit delayed Gaussian. So I guess that, now we have pressure loading, highly dynamic. It generates shock wave, which is elastoplastic shock wave that goes through the material. And at the end, we generate some residual compression in our affected zone. So now you know roughly the same as I do about laser shock peening. So now why we actually started with this, it was because of an application. We needed to support the guys who had the technology with a little bit of modeling, and they wanted to improve properties of cutting edge. Originally, I blurred the edges of this actual tool because of industry, but afterwards I got permission, so you will see the whole tool a few slides later. So we have a tool, we have a model, it's cutting edge from tooling steel, and this is a typical failure. When we use the cutting edge to generate the tool, the component, something breaks out, and they wanted to improve the properties. So a little bit about modeling. Basically, first, I would like to recognize the great contributions of a group from Ireland, because everything stands and falls with solid for foam. But we have some top-level algorithm because we need to apply multiple shots. So in a single shot, we have dynamic loading, which is this elastoplastodynamic wave going through the material. It plasticizes material, but it dissipates energy. So after some time, it ceases to plasticize the material. This happens in tens of nanoseconds. Then the laser is moved, which takes roughly 0.1, 0.2 seconds. So it's basically static relaxation for the material. So we take our plastic strains and we have static relaxation with a perfectly elastic material with prescribed internal state. And this is done in OpenFOAM, or mostly in little bit tweaked solids or foam. And then we have a little bit different boundary conditions that allows us to move the laser for different shots through simple Python. So that's it. And then, of course, we implemented the OpenFOAM because I'm here. But usually it's done, or similar stuff has been attempted since 2000, roughly, in finite elements with different level of success, but it's been done for 20 years in finite elements. So why we chose OpenFOAM or finite volumes first is because we know it, but that does not look good in the presentation. But what looks good in the presentation is that our research goal is to create a robust modeling framework. This is the whole part that we were interested in. So it's this cutting edge. And then, the consequences of this industrial is that our used meshes may not always be perfect. And at the same time, we have a elastoplastodynamic wave that is loading in tens of nanoseconds and in units of gigapascals. And we cannot have perfect mesh for this. Then we need efficient code parallelization, at least to some extent. And because this is in cooperation with industry, we need our codes to be open source because we cannot afford to have any licensing problems. So we keep the codes, but we need to be able to run it as we need, even on the machines of our partners. So that's it. And then finite volume versus finite elements. And well, main goal is, or main reason is that finite volume is somewhere we read that finite volume should be better for wave propagation through unstructured meshes. And yeah, we have this fine OpenFOAM tool available. Of course, there's this downside that finite volumes are not widely recognized in community. So anywhere I go with this, I need to convince them that finite volumes are okay. But here, everything is good. Everything was explained much better by Philip like 2 days ago. So we use their framework. So nothing here. We have a standard balance equation formulated in displacement, isotropic Hooke's law. Everything lives in small strains and small rotation. Everything is nice. We played with different approaches available in OpenFOAM, in solid form, but at the end, the simplest one, the segregated cell-centered, seems to be the most suitable for this case for some reason. But yeah, nothing really new here. What we did and played with a little bit is this inverse dynamic versus static balance. So we actually have two domains. One is for transient, so because the affected zone is fairly small compared to the whole component. So we have transient domain where the elastoplastodynamic wave propagates, and we have a static domain, which is the final part or final simulated part of interest. And we have two domain decompositions, and we needed to implement an algorithm that provides like direct one-to-one mapping from one domain to another, not to lose time through, well, not to lose accuracy through interpolation, and not to lose time through finding version default in this. Now a little bit about verification and calibration. We started with the simplest case in shock peening-like conditions. So we have a semi-space, which we load uniformly on top, and everything is elastostatic. So there is an analytical solution for this, like 100 years old from Business. And well, Business solution is actually for point force, but it can be integrated for some special cases to obtain analytical solution for plane strains or semi-analytical solution for rotational symmetry. But it's nice. And we have two testing lines. One goes close to the axis of symmetry inside the material. The other goes in the first layer of cells below the surface. And there we compare analytical to numerical solution. But because this is elastostatics, and we know that foam is able to do this quite well, so yeah, unsurprisingly, we get some acceptable results and mesh convergence. A little bit more interesting stuff is elastodynamic wave propagation. So we found analytical solution by Latourelle. The guy must have been a genius because he has once more a cylindrical, semi-space loaded with cylindrical load. It's a heavy side loading, and it generates a complex system of waves going through the material, and he derived analytical solution, which on the axis of symmetry is actually in closed form. So we were able to apply this in conditions similar to shock peening. And yeah, there is some dispersion that we encountered, but in altogether this was acceptable up to us first, and second, the guys that have finite elements available were not able to come up with anything better than this. So it's like good. And from our point, the good stuff is that after this we have this static relaxation. So if the wave does not plasticize too much at the wrong places, it helps us a lot. Then, yeah, to the actual laser shot peening, we have this elastoplasty plus elastostatics. We start with boundary condition, and we keep it simple. So our material is either perfectly linear elastic or or perfectly plastic, which is not physically correct because we have huge strain rates. But we kept it simple. We have a few parameters in our boundary conditions. And we have guys that actually have the technology and have the spare time to perform for us calibration experiments. So we have this cube. It's not in the scale. It needs to be half space for us to be simulated easily. So it's a cube 10 by 10 centimeters. And we have 1.5 millimeter radius spot in the middle. And the guys are able to measure residual tensions in there using some diffraction methods also. And we use these single spots to calibrate our model. And then we have small patterns on a different size. And we use these small patterns to validate the model. So for the calibration, yeah, we have 2 spots altogether because of the symmetry, 8 data lines. You can see this, well, points. It looks like a mess, but from the community, the guys were happy about this. Like, yeah, we have very nice data, and we spent like a year by preparing the cube to be perfect. So we have this nice spot. And then what we did here is we used just simple optimization algorithm to fit our response from the model. And what we needed to do, like perfectly plastic is completely wrong. So we needed to artificially harden our yield strength. But at the end, the agreement is quite good from our point of view, and it's somehow to some extent also mesh independent. But we said, okay, this might work, and we took a look at the pattern and find out that we did not break it. Like on the pattern, it works as well. So let's go back to the original problem. So our cutting edge from tool steel. This is how it's used roughly. So this is model for the cutting edge. This is the initial workpiece. We want this. And when we are pushing the material through the cutting edge, that is in the orange box, there is this concentration of stresses, and it causes this failure after some usage. So we applied laser shot peening, and there were 2 strategies. First was it breaks on top, so apply it from top. It's this row 1 and create pattern from top. And after some modeling and testing, we came up with also row 2, which is from inside of cutting edge. And the reason behind is hidden here. So this is the original part with lifespan 1. And then when we applied the strategy 1, these colors are by reduced residual stresses. So it's equivalent stresses, but these are the residual stresses. And you may see that this is inside the cutting edge, and that there is something almost not affected at all. And the lifespan of this part was falling from 1 to 1.3. The failure changed a little bit, but this was not usable anymore on the line. But we noticed that, this pattern on the right side is similar to this pattern on the left side. So we said, okay, let's find a direction from which we can reduce these spots. And we started from inside, and that contributed to prolonging the lifespan from 1 to 4.1, which was success for the industrial partner. Well, that's it. So just a few nice images at the end, what we have also available. So this is, we see the affected zone on this image. So it's using some thresholding on equivalent plastic strain. It's from row 1. And before you saw you saw the residual stresses on the surface of the material. So now you can see them inside. And when we apply the second row, the affected zone just increases quite understandably. One more information that is here, and it's because of this elastoplasty The blue here, you cannot see anything inside. It's mesh density, which was imposed by the dynamics of the problem. And the gray line, it's decomposition for roughly 100 cores. I should have brought water here. Well, this is Ah, comes here. Great. Thank you. And sorry for the delay. Okay. Now the conclusion should be interesting after keeping you waiting, but first, yeah, this is not only work of our institute. There were the guys from company Super Hard Materials that actually motivated this and kicked us around for 3 years to come up with the solution. So big thanks to them. And there are guys from another institute of Czech Academy of Sciences, from Institute of Physics, from the Haile Center that have the technology and the patience to run useless validation and calibration tests for us. So that's it. Then just a few code characteristics. Well, it's open source. It's based on OpenFOAM and Python. And at the end, we have our package, which is called PyLSP, and it's just installable through pip. So when we need to run it on on partner's computer, we just distribute pip package. And we know that the code scales well up to 96 cores, because that's as much as we have in single cell server. And that's it. Now the guys from Super Hard Materials came up with the idea that let's not use it to steels, let's use it to cemented carbide, which is heterogeneous material. So now we are playing with using this, numerical homogenization of our heterogeneous material. So that these are our next steps, but we will see. We have another 3 years to come up with that. So here, I would like to acknowledge the financial support that allowed the guys from Super Hard Materials to kick us around, and thank you all for your attention.
Nice work. Any questions? Quite a few questions we were thinking, and Python, how does that impact the OpenFOAM solver? It's studying it's doing the laser part, right?
Yeah. It's we have basically our like laser boundary condition and the Python, and then we have like it's simplified to set to just select the phases on which the pressure will be active in the next iteration, and Python is doing that. And also it takes care of some data transfer, because we keep a lot of data during simulation to see how, for example, we first put one pattern, then we put pattern with a slight transition, and we need to see the internal variables through that. So it takes care of this data transfer and of selecting phases.
So that the OpenFOAM solver start when the boundary condition invokes a Python interpreter, or calls a terminal command, or how does it develop? I guess.
It's Python is basically pre-processing. Then Python just says use this temporal profile, this spatial profile on these spaces, and then in foam solver we have basically it would be function object, but it's hard coded that tracks how many cells are still actively yielding. When this goes down, we stop everything. Then we transfer the plastic strain through Python from the dynamic case to the reference, to the static case, then start static relaxation from this plastic strain field.
So are there two meshes running in parallel and they're dynamic in the study?
Yeah, but both meshes are decomposed all the time. Just both two meshes are used, and the data are transferred through our mapper.
What's the mapper division?
No, it's C++. It's foam mapper. Well, it's foam. It has foam header. Yeah, that's the interesting part.
Any other questions?